Hey guys, this is chapter 20, part 3. This should be the last one in the series, I hope. So, introduce if we are calculating the cell potential under non-standard conditions. And what that means is if I have an electrochemical cell, but if the concentration of the ions is not 1 molar, then that means it's going to be at non-standard conditions. Most of the time, we're going to set it up with, like if we did this experiment in lab, our built an electrochemical cell, we usually use solutions that are like 0.1 molar, 0.2 molar, or whatever. Those are not standard concentrations, so we would have to calculate the value of E instead of E naught. So the way that works, our equation right here, E for the cell potential under non-standard conditions equals the E naught value minus RT over NF times the element Q. The values we use there, R is going to be the 8.314 joules per mole Kelvin. T is temperature in Kelvin. N represents the number of electrons. When we have the two half reactions and when we combine them, the number of electrons that are being transferred from one element to another in the balanced equation, that's going to be N. And then F is the Faraday constant. It's like 96,500 something. So with all those values, and then Q is my equilibrium products over reactants using whatever concentrations are given. So I can plug all those in. There's different forms of this equation. Instead of a natural log, if you want to use a regular log, there's a factor of 2.303 that has to be factored in. Again, it doesn't really matter which one of those you use, you just have to pick one. And then if it's 25 degrees Celsius, which is usually what we assume, if you plug in 298 Kelvin for T, that means R, T, and F are all now constant values that you can multiply them together. The simplest version of the equation is right here. E equals E naught minus 0.0591. That's just the accumulation of all the constants over N times the log of Q. So this is the version of the equation that we probably use the most. I think this is the one that's on the formula sheet. I won't give you a problem where the temperature is anything other than 25 degrees, so you probably don't need to worry about that. So, at 25 degrees Celsius, if we want to calculate the E value for a zinc copper voltaic cell, the copper concentration in the copper electrode, the concentration of copper ions in solution is going to be 3.6 times 10 to the minus 4 molar. In the other electrode, the zinc is going to have a concentration of 2 molar. Based on those concentrations, we should be able to set up our expression. So in the reaction, I've got my reaction. If I set up my equilibrium expression, K equals products over reactants, only aqueous ions are going to appear. So on my product side, the only thing that's going to appear in my expression is going to be the concentration of zinc. It's going to be on top. And then on my reactant side, concentration of copper ions are going to be on the bottom. So Q is going to equal the concentration of zinc over the concentration of copper. So Q will be 2 molar over 3.6 times 10 to the minus 4 molar. Divide those two numbers, that's Q. So I should be able to plug in. A few minutes ago, we already calculated the E naught value was 1.10 for this cell. That was earlier in the PowerPoint. The concentrations we plugged in right there for Q. And then finally, in this reaction, each zinc atom is going to give 2 electrons to the copper atom. So the number of electrons being transferred is 2. That's my N value. So once I plug all that stuff in, it's kind of like the Henderson-Hasselbalch equation, where if I have a buffer, the pH of a buffer solution is always going to be pretty close to the pKa value. When you change the ratio of the conjugate acid-base pair, it's going to make the pH go up a little bit or down a little bit from the pKa value. This is the same thing. The E naught for this cell is always going to be pretty close to the E value is going to be pretty close to the E naught value. Changing the ratio of these two things may make it go up or down a little bit, but it's going to be close to the E naught value. So E naught was 1.1. When I do all the math over here, I find that if I have a lot more zinc than copper, that's going to shift my potential down a little bit to 0.99. Okay, that would be the E for this cell as we constructed it if we hooked up a voltmeter, it should read 0.99 volts. And that brings us to our last topic, balancing redox equations. So if you were given a reaction like this is one we saw earlier in the PowerPoint when we were just assigning oxidation numbers. But if I want to balance this equation, this is a lot harder than when in 1211 in chapter 3, when we were balancing equations then, we had a pattern we followed where we just looked at how many atoms were on each side and we balanced it out and it just worked. In reality, when we do redox equations, we can't just look at atoms. We also have to consider the overall charge and the number of electrons present in the system. And we can't let the charge change when we move from left to right, because if the charge changes, that implies that electrons either appeared or disappeared out of nowhere, and that's not allowed. So we have to make sure that the atoms balance out and the charges balance out, and the only way you can do that is to follow a very specific procedure. There is more than one way to balance the redox reaction, but I'm just going to teach you one way. You need to practice it a few times until you can do it. On the test, you will have to balance a couple of redox reactions. The ones we've already done earlier in this PowerPoint are pretty easy ones. When it just shows metals, and like the zinc and copper one, that's an easy one to balance. You could probably eyeball it. But then if you look back at the one that was like zinc and silver, if you notice, we had to do 2 silver atoms to 1 zinc. If you weren't paying attention to the electrons, you might not have noticed that. Okay, so again, they're easy ones and hard ones, but you've got to go through this procedure so you can kind of get the hang of it, practice until you get it down. So first thing we have to do when we look at a redox reaction, if we want to balance it, is we have to recognize the 2 different half reactions that are going on. So in the one that's up here, one of the half reactions is for the oxidation of iron. Iron's going from +2 to iron +3. So I want to write a separate reaction just showing that process. Fe +2 yields Fe +3. That's going to be one half reaction. It's going to have some electrons in it, but we're going to figure that out as we go. But I'll write one half reaction, Fe +2 yields Fe +3. The other half reaction, I know the permanganate ion, MnO4- is going to become Mn +2. So that's going to be my other half reaction that I'm going to write. Once I have those 2 things written, I'm going to balance each one of them separately. I'm going to focus on one half reaction, get it fully balanced. Then I'm going to get the other half reaction fully balanced. Once I have them fully balanced, then there's going to be a procedure for how we put them together, and then I can simplify it down from that. So write down your half reactions. Balance each half reaction, but there is a procedure we have to follow. First of all, and again, we're going to do this in a minute on the chalkboard, but we're going to balance any elements that we have present in the half reaction other than oxygen and hydrogen. So like in the first reaction, we have iron. In the second reaction, we have manganese. So I would want to balance those elements first by putting coefficients wherever I need to. Once that's done, then I'm going to balance oxygen by adding waters on whichever side I need. Then I'm going to balance hydrogen by adding H pluses. Now, you might think, well, how can I just add water and H pluses whenever I want to? Well, normally these reactions are being done in an aqueous solution. And anytime I need oxygens, I can pull oxygens out of the water molecules. And if I need hydrogens, remember there's H pluses floating around in an aqueous solution. So those elements can be pulled in and out of the solution whenever they're needed, okay? So after I have the other elements balanced, then oxygen, then hydrogen, then I'm going to look at the total charge on each side of the equation. I'm going to balance the charge by adding electrons on whichever side I need the electrons. Specifically, when I have a half reaction and I look at the charges, whichever side the charge is higher or more positive, that's where I'm going to add the electrons, because the electrons are always going to bring the charge down. If both sides are negative, I'm going to consider the side that's less negative, it's closer to being positive, that's the high side. And then the side that's more negative is the low side. So I'm going to add electrons to the side that is either more positive or less negative than the other side. Finally, once I have both half reactions fully balanced all the way through to the charge, that's when I'm going to combine them. But I have to combine them in the right ratio, because when I do that step, the electrons have to cancel out. If you think about it, you have never balanced an equation where it had electrons floating around before. Like this chapter, when we've looked at half reactions, sometimes a half reaction will have electrons. But when you put them together, the overall reaction does not have electrons. The electrons have to cancel. And then finally, once I combine them in the right way, the electrons should cancel out. But then if you see anything else that appears on both sides, like sometimes you'll have 2 water molecules on one side and 5 water molecules on the other side, you're going to reduce that down so that the 2 would go away. I take from the other side where there's 5, I take 2 away and end up with 3 waters. I'm always going to simplify it down so that I don't have anything on both sides. And then finally, one more step. If the problem specifies that the solution is basic, then I'm going to actually add hydroxides to get rid of the H pluses to make the solution more representative of what would be present if I had a basic solution. Again, I only do the last step if the problem tells me to make it a basic solution. We'll see that in a few minutes. So, actually, let's do the one on the first slide. So I'm going to cut off the PowerPoint. Actually, I'll just do another video, and we'll balance 2 or 3 equations, and then we are done with chapter 20.